Now let's take a look at some of the most common functions for working with factors. There are many more functions than these for working with factors, as you will see later in the course, but this handful of functions will provide you the tools to do much of what you will need to do with factors. Let's begin by reading in the Mount Juniper elementary data. Let's take a look at these data. So we have characters for first name, characters for last name, characters for gender, numbers for grade, and numbers for score. Gender and grade should both be factors. Gender is a categorical variable. In fact, it's an unordered categorical variable. Grade is also a categorical variable, but that one we could put in order. So let's get our data to look the way we'd like it to look. I'm going to start by making grade level an ordered factor. The isFactor function can tell us whether a vector is a factor. So let's do isFactor for the grade vector of the Mount Juniper data. We get true. It is a factor. We just made it one. If we want to get more information on all of the vectors in our data frame, including factors, we can do that with the structure function, str. Now take a look at what this tells us. First name is a character vector, last name's a character vector, gender's a character vector, and grade is an ordered factor. Remember, we just changed it to become an ordered factor. Score is numeric, it's an integer. Now, interestingly, and a little bit annoyingly, the readCSV function will turn a character vector into a factor or not turn it into a factor depending on the version of R. And this was a recent change with version 4.0. I believe it's version 4.3 or 4.03 installed on my system. And so mine might behave differently than yours if you have, say, 3.9 or 3.8 installed on your system. The reason this is unfortunate is because we can write scripts with an expectation that it will work a certain way, but it will work differently on different computers. So we need to be careful about this. We can check whether or not the readCSV function will turn a character vector into a factor with this function, default strings as factors. Note mine says false. What that means is when it recognizes a character vector, it will leave it that way. That's why if you look at my data frame, first name, last name, and gender are all characters because R leaves them as characters when using the read.csv function. If we were looking at 3.9, that might be the case with your R implementation, and so you might be seeing different results. Let me show you what it would look like. And the way I can show you that is to show you what it looks like when we use an argument here on line 183 on my code. Strings as factors equals true. That means that whenever we use the read.csv and it sees characters, it will turn it into factors. Watch. So I'm going to reread in the data. And now let's look at the structure. Now first name, last name, gender have all been turned into factors. Grade has not because R thought these were numbers, so it left them as numbers. So if you actually see this with your structure when you use read.csv without putting in this argument, that means you have an older version of R where strings as factors equals true was the default. Now strings as factor equals false is the default. So that's why, because strings as factors equals default on my system, when I read in the Mount Juniper data using read.csv, it left all the character vectors as character vectors. Now, which way is better? The reason that it was changed with the newer versions of R is that it usually is better to keep characters as characters unless we explicitly tell R that we want it to be a factor. So the R core team finally decided we shouldn't automatically change things unless the user wants that. So let's go ahead and change it back to the way that it should have been. And note that what I'm doing here, you could now do on any implementation of R and you'll get the same result. That is, I'm explicitly saying strings as factors equals false, which on my system is the default. On yours may or may not be. On other people's certainly may not be. But if we always put it explicitly, then we'll know that it will behave the way we expect. So that's the way to avoid trouble. So I'm going to put in strings as factors equals false. And now when I look at this, I get character vectors for first name, last name, and gender. Then, of course, integer for grade and score. Now, I'd actually like gender to be a factor. So here's how to keep some vectors as character vectors, but not others. Look what I'm doing now when I'm reading in. I'm using as is equals, so this is a new argument, as is, and I'm using a vector that is as long as the number of variables I have. I want the first name to be left as a character, so I'm putting leave it as is, true. Last name, leave it as is. Gender, false. Go ahead and turn that one into a factor. Now, grade is an integer, so saying false isn't going to make it a factor. So I'm just going to leave these last two true. So let's go ahead and see what we get. And now we have gender as a factor, but we have to take one more step and turn grade into an ordered factor. And I'm going to label it third, fourth, and fifth instead of 3, 4, and 5. And now we have exactly what we need. So this is some elementary data cleanup, making sure that each of the vectors in our data frame are of the class that we expect them to be. The table function provides counts of factor values. So let's get a table for Mount Juniper grade. Third grade has 57, fourth has 74, and fifth has 69. Let me go ahead and check these. Notice how I'm doing it. I'm summing the 57, 74, and 69 to see if it equals the length of the Mount Juniper grade vector. And it does. We can use the cut function to create equal interval categories from a quantitative variable. So we have this variable Mount Juniper score right here. So let's use the cut function in order to break this up into 3 different intervals. Let's take a look at the table. So here are the equal intervals that it figured out based upon our scores. 46.9 to 66.3, 66.3 to 85.7, and 85.7 to 105. Now, if you look at these headings, you notice an open parentheses and a closed. Let me make sure you understand what those mean. The open parentheses means this value is not included in this interval. The closed parentheses means that it is included. And so if you look here at the end of the first interval is 66.3, the beginning of the second is 66.3, but we know that if it ever encounters a score of 66.3, it's going to go in that first interval because the closed bracket tells us 66.3 inclusive, whereas the open is exclusive. So here in that second interval, it's 66.3 exclusive. Now we stored this cut into Mount Juniper score level. Note that this new variable is a factor with the cut points as labels. So here it is, score level, factor, and the labels are those cut points. We could actually use the levels command. And there they are. Now these are equal intervals, but we might be more concerned about having nicer breakpoints. The pretty function will help with that. So here I'm going to cut, but I'm going to cut based upon what the pretty function says about how to cut. Let's look at the table. Now we have 40 to 50, 50 to 60, 60 to 70, and so on. If we want, we can specify our own intervals. This has taken me from 45 to 75 and 75 to 105. Notice the minimum and maximum and what happens if I don't include some scores in my cut. The minimum is 47. The maximum's 105. Let me create cuts from 50 to 75 and 75 to 100. Let's take a look at the data. I'm looking for the minimum or the maximum, 47 or 105. Here's the 105. Notice that missing data was put for the score level. We can change levels. So let me go back and cut it so that I am sure that the scores are included. Here we go. And now let's make those levels low, medium, and high. Now you see we have score level is a factor with 3 levels, low, medium, and of course high is in there as well. Let's get the table. There you go. This is an ordered factor, but we've already created the factor. Can we indicate that it's ordered after the fact? Of course we can. So here I'm going to take the variable, Mount Juniper score level. I'm going to use the ordered function. Now let's look. Now we see it's an ordered factor. Notice that this time, the sum of the frequencies still don't match the length of our vector. Why not? It's because we have missing values. This time I'm going to use a function called complete cases. I'm going to take my Mount Juniper data and I'm going to get complete cases for Mount Juniper. Notice that I now have 183 observations. Any row that had missing data anywhere was excluded. So now if I get the sum of the tables of the score levels and compare it to the length of the vector, I get true. They're the same. Let's see how to lump together medium and high so that we only have low and high. Look what I'm doing. I'm going to use the subsetting function. I'm going to get for Mount Juniper score level all the score levels that are equal to medium, and I'm going to assign them high. Now that's fine, except medium is still a factor. We can eliminate that with the drop levels function. So Mount Juniper's score level, drop levels. It will only drop any levels that doesn't contain any data. That's more like it. So to review the common factor functions, we can check that a variable is a factor with is.factor. We can use string to see data structure that includes factor information. The read.csv function will use the strings as factors argument to determine whether character vectors are factors. And remember, you can use the default .stringsAsFactor function to see what the default is. You can alter the read.csv function factor creation with the stringsAsFactors argument and the as-is argument. The table function will count factor elements. The cut function will create a factor from quantitative data. The pretty function will create friendly interval breakpoints. The drop levels function will drop a category that has no elements.